And hello AP Physics students, day 3, homework number 3 coming at you here. Motion with constant acceleration coming at you today. Gonna talk about freely falling objects as well as dive into our first equation sheet. Oh, so much good stuff coming at you here. Okay, let's talk about sections 2.5 to 2.8 a little bit, alright? Section 2.5 contains probably the 3 equations you are going to use the absolute most this year, okay? These 3 equations are called motion with constant acceleration equations. And as the name applies, in order for these 3 equations to be true, your acceleration must be constant, okay? Now, what do the symbols in these equations mean? Well, here, anytime there's a little 0 as a subscript, we call that naught, so this is V naught, and that means initial. So V naught would need initial speed or initial velocity. A variable without a little naught there means final. So this is V naught, meaning initial speed. This is V, meaning final speed. Notice A, acceleration, does not have an initial and final because the acceleration is constant. Must be constant. T is time. X is position. A is acceleration. This would be final position, initial position. We sometimes write this as delta X, meaning change in X or change in position. Okay. Now your book goes through and derives these equations from the definitions of acceleration and velocity, and you don't have to be able to do that, but you do have to be able to know how to use those 3 equations forward and backwards. As a matter of fact, your book fits a 4th equation in here, but you don't need the equation. You can derive it from the other 2. Okay? So that is section 2.5. Section 2.6 is good to read. It's about problem-solving strategies. And then 2.7 talks about freely falling objects near the Earth's surface. So Galileo, way back when, figured out that freely falling objects near the Earth's surface fall at a constant acceleration. And that constant acceleration we now call little g, meaning 1 unit of Earth acceleration. And it is equal to 9.80 meters per second per second. Now that value changes a little bit based upon things like your altitude and what the geology of your local region is like. And while g is always aimed downward, and many times when you plug the g into an equation, it may end up having a negative value, g itself is a positive value. We just say the acceleration due to Earth's gravity is a positive 9.80 meters per second squared. And depending upon how you define your coordinate system, it may get a positive or negative number. Okay? By the way, what is a freely falling object? It is an object that is falling where the only influence is the Earth's gravity. So if it's an airplane or a rocket, it is not a freely falling object because you have things like, the engines of the rocket or the wings of the airplane exerting influences, later called, in next chapter we're going to call those forces, on the object. So, to be a freely falling object, the only influence or force acting on you is the Earth's gravity. Alright? Well, let's do an example problem using the 5 problem-solving steps, solving a kinematics equation of 1 dimension using just these 3 equations. By the way, Mr. Curson, do I ever have to memorize these equations? For the free response section of the AP test and for my quizzes and tests, no, you do not. They are right here on your AP equation sheet. You can use this equation sheet on all my quizzes and tests and on the free response portion of the AP test. Unfortunately, you can't use it on the multiple choice portion, but we'll talk more about that later. And if you haven't gotten one of these equation sheets in class yet, make sure you ask for one tomorrow. Okay? So, first 3 equations on the equation sheet we're going to use to try to solve this problem. And the problem is number 27. And the problem, as I read it, goes something like this. I have a car, and I'm driving along in my automobile here. And the car initially is traveling at 85 kilometers per hour. And then, that's kind of the before, and then afterwards, the car, so this is my initial conditions, and then in the end here, the car crashes into this tree, right, and the front end gets all messed up, all right, and the final velocity is 0 meters per second. And we're told that as the car is crashing, the hood collapses about 0.8 meters. Okay, so the car crushes 0.8 meters as it's coming to a stop. So we're guessing this is occurring over a very short period of time. Probably expecting a high acceleration, right? This is like 50 or 60 miles per hour going to 0 miles per hour in a very quick time. All right, so we want to know what the acceleration is here because that's what the problem is asking. I know the initial speed, I know the final speed, I know the change in position. Which of these three equations might I use to solve for acceleration? Well, I could use this equation, except I don't know acceleration and I don't know time. And it would be hard for me to use that equation if there's two variables I don't know. Likewise, this equation has acceleration and time in it, two variables I don't know. So that equation's not going to help me very much. However, this one, I see I know all of the variables in it with the exception of acceleration, which is what I want to know. And we know from math classes that you can usually solve an equation if there's just one thing in it you don't know. So I'm going to write that equation out here. So I know the equation that I'm going to work with. And then I am going to wave my magic algebra wand at this equation. And I am going to solve it for the variable that I want before I plug in numbers, right? See, wasn't that pretty easy to solve for A using variables before I start throwing numbers around in there and getting my numbers all confused? Okay, now I'm now going to check and make sure all of my units have the same unit on them. Pardon me, all my variables. Now I notice that this V naught is in kilometers per hour, but yet this X is in meters. Wow, I better do something with these units. Just to make things easy, I'm going to convert 85 kilometers per hour into meters per second. And you guys have had a couple days practice at this by now. So this should be old hat. All right. And if I solve here, I'm going to get 23.6 meters per second. Now, one thing I did not do, which I should have done earlier in the problem here, is define a coordinate system. I am going to say that moving to the right in this picture is the positive direction. So V naught here should have a positive sign because the car is initially moving to the right. V doesn't have a sign, and that's it for signs there. Okay. So if I go ahead and plug in what I know into this equation here, I'm going to get 0 squared minus 23.6 squared divided by 2 times 0.8. And again, this change in X is the car moves to the right as it's being crunched. So that's going to be a positive 0.8. And if that should be my A then. Okay. And if I plug all those numbers into my calculator and round to the correct number of significant figures, I would get that A is equal to negative 350 meters per second squared, which is a big acceleration. notice the acceleration here has a negative sign, meaning the person's acceleration is going to be to the left, right? The person is moving to the right, but they are slowing down, so the acceleration is to the left or in the negative direction, right? The final thing the problem asks us to do here is to express this acceleration in terms of g's, all right? If I take 350 divided by 9.8, better make sure that's on the screen, all right? That would be approximately 36 g's. In other words, the acceleration of this person while they're in the car is 36 times the acceleration of the Earth's gravity. In general, human beings can take about 5 g's worth of acceleration and usually be okay. Usually at 10 g's, some type of injury or passing out occurs. 50 to 100 g's worth of accelerations, usually you're not going to make it. So this is kind of, this person may or may not survive this collision. Certainly at 36 g's, they would be in some bad shape. Well, I went a little over my time here, physicists, but to reward you for hanging in there, I have an extra special treat for you. For hanging in there so well, I am going to give you, physics students, a bacon strip, bacon-flavored treat. There you go, physicists. Way to get a bacon-flavored treat for your hard work on this problem. Yes, way to go. Here's your bacon-flavored treat for doing so well on this problem right here. Nice work. Yep. Oh, good job. Oh, sorry, physicists. Your bacon-flavored treat got stolen by Raven. Oh, my gosh. Oh, I guess you don't get a bacon-flavored treat, but, oh, gosh. Oh, good work, physicists. We will see you tomorrow.